Welcome to the Deep Dive. So if you're a master's student in digital sciences, maybe specifically at TH Köln, and you're thinking, okay, how do I actually do scientific research? Well, this deep dive is definitely for you.
Yeah, our mission today is pretty focused. We're going to unpack the essential definitions, the language, the structures you really need to get your head around for proper computer science research, especially for that thesis.
Right, it's like setting up the foundations before you build the house.
Exactly. Think of it as understanding the rules of the game before you play.
And we're starting right at the beginning. Language.
Yeah.
We need to agree on terms before we can even research them. So, let's talk about the semiotic triangle. Ogden and Richards.
Ah, yes. Fundamental stuff. It basically shows that a word, the sign or symbol, it doesn't just point directly to the thing out there in the world.
There's an intermediary step.
Precisely. It's mediated by the concept. The idea in your mind, that connection between the symbol and the thing is indirect.
And that's where the problems start, right? Ambiguity.
Huge problems, potentially. Think about everyday tech terms. You say bug.
Could be an insect, could be a coding error. Context is everything.
Or model. Is that a machine learning model? A statistical one? Something else entirely? If your reader picks the wrong concept,
Then your whole argument falls apart. They can't verify what you even mean.
exactly. So rigor in defining terms isn't just nice to have. It's the absolute first step for any kind of scientific validity, which brings us past vague signs towards actual usable definitions.
Okay, and the sources mention two main types we need to know, extensional and intentional. Extensional seems straightforward, just listing examples.
That's the gist of it, yeah. An extensional definition just enumerates. So for sorting algorithm, you'd list bubble sort, quick sort, merge sort, and so on, defines by membership. But that feels incomplete. What if I invent a totally new sorting method? The list is instantly outdated.
You've hit the nail on the head. That's its weakness. And that's why, for scientific work, we really rely on the intentional definition.
Okay, intentional. What's the core idea there? It provides the complete set of necessary shared features, the properties that every single instance of that concept must have. It defines the essence, not just the examples.
That sounds much harder,
Okay.
especially in fields like AI where things change so fast.
Mm.
Do we have to redefine algorithm every 6 months?
Ah, that's a really good point. It highlights the tension, doesn't it, between the cutting edge and academic stability. For established terms like algorithm, the intentional definition holds. It's timeless. A finite sequence of well-defined, unambiguous, executable steps.
That core definition doesn't change.
Right. But if you're working on something brand new, part of your scientific contribution might actually be proposing and justifying a rigorous intentional definition for it.
I see. So it's not just agreeing these things are algorithms, but agreeing that anything meeting these criteria is an algorithm.
Precisely. And that leads us neatly into a formal method for doing this. Definition by genus and differentia.
Okay, break that down. Genus and differential.
Think of it like building a taxonomy. You define something first by its broader category, that's the genus. Then you specify what makes it unique within that category. Those are the differentia.
So for algorithm,
Yeah.
the genus is maybe a sequence of steps.
A sequence of well-defined steps, yeah.
Yeah.
And the differentia would be things like the steps must be mechanically executable, it has to terminate, it produces a specific output, it carves out its unique space.
Okay, that makes sense. We secured our terms. Let's zoom out. What's the bigger picture? What is science?
Good question. The Britannica definition gives us a solid starting point. Any system of knowledge concerned with the physical world and its phenomena, and that entails unbiased observations and systematic experimentation.
Looking for general truths, fundamental laws.
That's the core idea, and the way we do that is through research.
Right, and our sources define research as, let me check, a structured inquiry that utilizes acceptable scientific methodology to solve problems and create new knowledge that is generally applicable.
That generally applicable part is key, especially for a master's thesis. It's not just solving one specific problem for one context.
It has to add something to the wider pool of knowledge, something others can use and verify.
Exactly. And to achieve that, your research has to tick certain boxes. It must be rigorous, systematic, goal-oriented, solving a problem. And crucially, it has to stand up to critical scrutiny. People need to be able to check your work.
If the methods aren't clear and systematic, the results aren't verifiable.
And then it's Well, it's not really science. It might be development, it might be exploration, but not rigorous research in the academic sense.
Okay, so if the goal is this verifiable, generally applicable knowledge, we need different approaches depending on what we're trying to find out.
Correct. We need a way to classify research based on its goal. Our materials suggest about 4 main types.
Right. There's exploratory research
Yeah, when you're just starting to understand a new area, getting initial insights.
and explanatory research.
That's about understanding why. Looking for causes, relationships, maybe interpreting texts or systems.
And then the big one for many digital science students, constructive research.
Absolutely. This is where you're actually building something new, a product, a process, an algorithm, a technique. It's about innovation.
And there's also secondary research, which is reviewing existing work.
Like literature reviews or meta-analyses, processing what's already out there.
So within computer science areas like algorithms, AI, software engineering theory, databases, networks, graphics, all that stuff,
Yeah,
the method we choose has to match the goal.
precisely. The goal dictates the tool, and the sources highlight 5 common research methods in computer science. You want to run through them?
Sure. First up, experimental research. This feels like the classic lab coat approach.
Kind of. It's about controlled experiments. You manipulate variables, measure outcomes, collect quantitative data, think evaluating encryption algorithm performance under specific conditions.
Okay. Then there's simulation and modeling.
Right. You use this when the real system is too big, too complex, maybe too dangerous to experiment on directly. Like simulating malware spread in a network, you build a computational model.
Makes sense. And sometimes it's just math, algorithm analysis.
Pure math, exactly. Proving things about algorithms, time complexity, space complexity without necessarily running code. Analyzing sorting algorithms theoretically for huge data sets, for example.
And we can't forget the humans, user studies, and human-centered design.
Crucial if people interact with your system. Usability testing, understanding user needs, getting feedback, evaluating, say, no-code platforms for usability.
Now, a lot of these seem to fall under a broader category, empirical research, research based on observation or experience, collecting data.
Yes, empirical methods are very common. And the key distinction here, the one students often wrestle with, is qualitative versus quantitative.
Okay, let's break that down. Quantitative first.
Quantitative is about numbers, large amounts of data, objective measurements, statistical analysis, testing specific hypotheses you've set beforehand. Think logging system performance, running large surveys with closed questions.
And qualitative.
Qualitative is usually about understanding meaning, context, subjective experience. Typically uses smaller amounts of data interviews, observations, analyzing open-ended text. It's often more inductive. You build theories from the data.
But if it's subjective, small scale.
Yeah.
How is that scientifically rigorous? How is it verifiable?
That is the million-dollar question. Qualitative research is rigorous when its goal is about depth of understanding, exploring complexity, or maybe generating hypotheses for later quantitative testing. The rigor comes from the systematic way you collect and analyze that rich, non-numerical data.
So it's not about generalizing findings statistically to a whole population.
Not usually, no. It's a trade-off. You sacrifice statistical breadth for depth of insight. Choosing between qual and quant depends entirely on your research question. What do you need to know? Deep why or measurable how much?
Got it. Okay, let's pivot to something super relevant for students building things. Design science research, DSR.
Yes, DSR. This is a really important framework, especially in fields like information systems and increasingly practical areas of computer science. It's specifically about the creation and evaluation of IT artifacts.
IT artifacts. So that's the thing you build. The software, the model, the method.
Exactly, the purposeful solution entity. And DSR structures how we do that scientifically. It explicitly connects the act of building to the creation of knowledge. It hinges on understanding 2 types of knowledge.
This is the omega and lambda bit.
That's it. Omega is the existing general knowledge base. Think established theories, frameworks, proven methods, the stuff the scientific community already accepts.
Okay, and lambda.
Lambda is the project-specific knowledge, the unique constraints, context, data of the particular problem you're trying to solve right now.
So if I'm building, say, a new privacy protocol for smart home devices, omega would be existing cryptography principles, network protocols.
Right. And Lambda would be the specific limitations of those devices, the user requirements for that smart home setup, the particular threats you're worried about in that context.
Makes sense. So what's the goal of DSR in terms of omega and lambda?
The scientific goal isn't just to build an artifact that works for Lambda. It's to use the process of building and evaluating that artifact to contribute something back to Omega, to improve the general knowledge base.
So you end up with Omega plus what you learned from Lambda.
Ideally, yes. The process is usually iterative. You analyze the problem, using n and defining low. You design a potential solution, the artifact. You evaluate how well it works, and then you diffuse the knowledge gained both about the specific solution and any generalizable principles back into A.
Analysis, design, evaluation, diffusion. Okay.
Yeah.
This framework, these methods, they all need to end up in a structured format for, say, a master's thesis.
Absolutely. All this thinking has to be communicated clearly, and there's a pretty standard structure for scientific papers, including theses in computer science, usually 4 main parts.
Let's run through them. Section 1, Introduction.
Critical section. You set the stage. Background, context. You must clearly state your research question or hypothesis, and you need the literature review here, showing what's known and justifying why your research is needed. What's the gap?
Makes sense. Section 2, Methodology.
This is where you declare how you answered your research question. What approach did you take? DSR. Experimental. Empirical. If empirical, was it qual or quant? Why did you choose that method? You justify your choices here.
Total transparency. Section 3, Results Discussion.
Right. And it's discussion, not just results. You present your findings, sure, but then you interpret them. What do they mean? How do they compare to what others found? Linking back to your lit review. And crucially, what are the limitations of your work? Honesty is key.
Good point. And finally, Section 4, Conclusion.
Wrap it all up. Summarize the main findings. Clearly state your specific contributions to knowledge. What are the implications? And what's next? Suggest avenues for future research based on what you learned.
Okay, so we've gone from the basic building block, the meaning of a single word via the semiotic triangle, all the way up to the structure of a complete scientific contribution.
It's quite a journey. But mastering these definitions, these methodologies, understanding why they matter, that's absolutely essential for starting your master's research on solid ground.
And maybe the most practical takeaway for someone starting out is what you said earlier.
I think so. Your choice of research method, whether it's experimental, empirical, DSR, whatever, it must logically flow directly from the research question you stated right at the beginning in your introduction. If the question is, how effective is X, you need evaluation, probably experimental or quantitative. If it's, how can we build Y, you're likely looking at DSR.
That alignment is non-negotiable.
Absolutely. And maybe a final thought to leave you with as you plan your own thesis.
Go for it.
Remember, the goal of research, especially DSR, is often framed as contributing back to that general knowledge base, Omega. So always ask yourself, what specific part of my project, maybe it's a model I developed, a new way I measured something, a technique I formalized, what piece is robust and general enough that it could actually leave my specific project context, Lambda, and become part of Omega for the next researcher to build upon?
That's the real measure of impact, isn't it? Moving beyond just solving your problem to actually advancing the field.
That's the ambition. That's how you make a truly significant contribution with your master's work.